Why don't we start? So, hello everybody. My name is Pedro Diniz. I'm one of the co-organizers of this series of talks on quantum computing. And today it's my pleasure to welcome Ryan LaRose to our series. And so I'll start with a brief introduction here. Ryan is at this moment, or right now, a PhD candidate with the Michigan State University in Michigan, obviously. And he has been a contributor to Cirq, which is programming language or system environment, when we're going to hear all about it, and the development at Google Quantum AI. So today is a little bit more of a, I would say, nuts and bolts, if you will, or programming lectures. So we thought that this would be interesting because it gives you a little bit of more of what do you do or how do you program these quantum machines rather than looking into the physics aspects of it. And I also asked Ryan to give us a brief introduction of what's going on at Google AI quantum initiative, so to speak. Okay, Ryan, thank you very much for your availability and for the opportunity to hear what you're doing at Google. Thank you. Take it away.
Great. Thanks a lot, Pedro, and all the organizers of this event for inviting me. And thanks for everyone for joining. Like Pedro said, today I'll talk about Cirq and sort of how you can use that for a lot of reasons. You might use it to maybe learn more about quantum computing. You might use it to program a quantum computer or sort of anything, doing research and development. So it's always a little hard to gauge the audience, especially with virtual seminars. So if I'm going too fast or going too slow, please note this in the chat and please ask questions as I go through. It will be sort of a nuts and bolts talk after the first introduction, specifically just about how to get started with Cirq and what you can do with it. So there's a chance for a lot of questions, and I'll try to monitor the chat and make it so the talk is as useful as possible. So the agenda, what I have planned out is just as follows. I'll spend a short 5 minutes or so talking about just sort of all the software that's available, what has been developed by the Google AI Quantum team, and ranging from chemistry to machine learning to hardware access and things like that. And then I'll get into the nuts and bolts part. So I think getting through these 2 tutorials is probably all we'll have time to do. And if there's any time at the end, I can briefly highlight this last one that I have listed here. So the first tutorial is sort of a how to get started in Cirq. It's not the hello world of Cirq, it's the next tutorial essentially, but I figured this would be good to give the introduction, and also good if you've already seen Cirq before, and there will be a few things in here maybe you don't know. And then after this, I figured it'd be good to talk about noise and simulation. So simulating noisy circuits is a common task nowadays, and Cirq has a lot of nice features for doing that. So that will be the topic of the second tutorial. The last thing, ReCirq, I'll mention what that is. It's another sort of repository, research using Cirq, ReCirq. And this is where all of the publications that come out of the Google AI Quantum team, such as the Fermi-Hubbard experiment or the QAOA experiment, etc. They all have a sort of corresponding code that lives in ReCirq, which allows you to reproduce the results and really dig in and understand more what's going on in the code, sort of using Cirq. So that's really nice, and I'll at least highlight that, but we probably won't have enough time to go through that. So it will help to know the sort of basics of quantum computing, which is to say qubits, gates, channels, and circuits. I'm told that maybe not everyone is familiar with this, so that's fine. I'll spend just a little more time explaining, for example, gates when we get there. And it will be helpful if you've seen Python before, but also not mandatory. Cirq is a Python package. So with that, let's get into the main part of the talk. So the software stack is sort of nicely displayed by this image, and your landing page for all things Google Quantum AI now is this website, quantumai.google. So this is where I took this image from, and this is showing off the software stack, but there's a lot more on the website. I'll flash it briefly after this, ranging from research to hardware to education, other open source stuff, getting involved with developing the open source libraries, and similar things. But let's focus on the software. So we see Cirq at the center. And Cirq is sort of the programming framework that you use if you want to use the quantum computing service. So that's down here. You write your quantum circuits in Cirq, and then you can send them to the service. And then on top of that, you have all these sort of additional libraries and extensions. OpenFermion is one for chemistry. TensorFlow Quantum is one. If you're familiar with TensorFlow, you might guess it's for machine learning. And then the other highlighted one here, QCim. QCim is a very highly optimized quantum circuit simulator. So Cirq itself has, of course, the ability to simulate circuits. And if you are trying to simulate large circuits, QCim is a good option to do that. There's also a lot of third-party integrations, some of which I might mention in this talk, but they're all listed on the website. So let me quickly show the website. It looks like this. This is the homepage. Explore the possibilities of quantum. You can explore Cirq, or you can explore the hardware. So here are the sort of tabs. The website, by the way, is relatively recent, like in the past 3-4 months, I think. And all the documentation for all the open source software now lives here. The old place was Read the Docs, and that's been retired for this. But I just want to flash this. You see some of the things I'm talking about now: Cirq, OpenFermion, TensorFlow Quantum. And then if you want to dig in later, the quantum computing service, which I won't mention too much, but you can read these things and all of that fun stuff. So the main page for our talk will be the software page, and spending most time on Cirq, and then I'll mention some of these other libraries at the end. So the homepage of Cirq gives you the documentation, and these tabs here are sort of where you need to go to find out what you need. So the overview, that's where we are now, and you can sort of get the Hello World program of Cirq. This I'll discuss more in the tutorials, but you can at least see it now. And then there's two things which I want to mention. There's the guide. The guide is sort of first steps and essential concepts, and then one step beyond that. So sort of the documentation, this is where you want to start if you're first looking at Cirq, or if you want to know how to do a particular thing inside Cirq. So for example, installing here, and then later, the first tutorial I'll mention is the gates and operations one. The other thing is tutorials and examples. So these are particular things that have been done in Cirq. And this maybe relates more to papers that you might read or research that's being done. For example, a variational algorithm. These are common things in literature, and you can see how that's been done in Cirq and how to do that here. Also, more standard tutorials, but are maybe more involved, like Shor's algorithm. There's a tutorial on that. And the other one's here. And then you can see a bunch more examples on the Cirq GitHub, which is linked here. So this is the sort of overview of all the docs. And now I'll pretty much just be going through some of them. And I've sort of handpicked them to hopefully be the most useful, like I said, for this talk. So if I go to the next slide, the tutorials that I wanted to talk about here were gates, gates and operations, and then custom gates. So if you haven't seen this picture before, this is the sort of circuit model of quantum computing. And you read it as follows. We start at the left and time proceeds to the right. And we start with some qubits here labeled A, B, and C. We have 3 qubits. And then these wires just denote sort of time, evolution of the qubit. And then there's gates represented by these boxes with symbols, which are what happens to the qubit. So here we do a Hadamard gate on the qubit labeled B, a C0 gate, and etc. So that's just sort of background. This is nothing Cirq specific. And then the Cirq specific stuff is what you see highlighted here. So moments, and then there's a discrepancy between, or a distinction, I should say, between gates and operations in Cirq. So I will now explain that in the tutorial. The guide, I should say. So one more note about the guides. At the top here, we're on the website now, and I'll zoom this in a second so it's easier for people to see. But there's a really nice feature about all the guides. We'll see code in them, and code is something you run, so it's nice to be able to run this. And you can do that by clicking at this top here, Run in Google Colab. So there's a button on all the guides and all the tutorials, and if I click that, you'll see this tab open here. And we now see the same guide, but it's in Colab. And if you are not familiar, Colab is just sort of an online Jupyter Notebook environment by Google. And it allows you, it's the same content, but it allows you to run these things. So for example, I can run through these cells. It might ask me to sign in because I'm in a private mode on Chrome. But you can see the code here, you can edit it, you can change things, you can play around, and you can actually run these and see how it works for yourself. So I just wanted to mention that, and now I'll explain gates and operations in Cirq. So every tutorial starts with this install. So we're trying to import Cirq, and if we can't, then we install it. And then here's the same diagram that we've seen in the slide. And now let me explain the Cirq part. So like I said, there's a distinction between gates and operations. Gates are sort of qubit independent. They have nothing to do with qubits. It could just be a Hadamard gate or any other gate. Here, a Hadamard gate. Operations are gates acting on qubits. So whenever you have a gate acting on a qubit, here B, we call that an operation in Cirq. And then the circuit itself is composed up of moments. And a moment is a set of operations happening all at the same time or in the same moment, hence the name. And a circuit, like I said, is just a collection of these. So there's this hierarchy starting at gates. Gates act on qubits to form operations. Operations get collected into moments, and then a sequence of moments is a circuit. Great. So in quantum computing, there's a set of standard gates that you sort of assume. Things like the Hadamard gates, the controlled NOT gates, and measurements. So after explaining how it sort of works syntactically in Cirq, that's what the rest of this tutorial is about. So we can go through it pretty quickly here. I'll show you how to create a circuit. The first place to start in our sort of hierarchy is qubits. There's several types of qubits in Cirq. For example, we could use a named qubit. A named qubit is just a qubit that we give a certain name to. And that's what we use in this example here. So to create a named qubit, you can do cirq.namedQubit, and then you give it a name. So this qubit has a name A, and that's sort of how it's referred to and what sort of uniquely identifies it. In practical hardware, we usually have these sort of 2D architectures, at least now. So there's also what's called a line qubit, and this is just a qubit that lives on a line. So it's specified by one index, for example, 0, 1, or 2. And then also common is this 2D architecture, so we can have grid qubits. you can probably guess by now, but a grid qubit is a qubit that lives on a grid. So it's specified by two coordinates, say an X and a Y coordinates, just sort of its Cartesian pair. But for now, let's use named qubits. We create 3 named qubits here, A, B, and C. And then we see some example operations. So Cirq.h itself is a Hadamard gate. A Hadamard gate takes you sort of starting from the 0 state, gives you an equal superposition of the 0 state and the 1 state. So here we have a Hadamard gate acting on the qubit we call B. So this is now an operation, and if we print it out, we see its representation in Cirq, which is just a useful thing, H acting on B. We could also do C0 acting on B and C. So the convention here, the qubit order, is the usual thing that the first qubit is the control and the second qubit is the target. So if we look back up at our diagram, this corresponds to this operation here, C0 controlled on B with C as the target qubit. And so on, you see sort of remaining operations in this circuit. And to wrap them in a circuit, I don't know if it actually does it in this tutorial, but to wrap it in a circuit, pretty much all you would do is create a circuit. I'll show this in the next tutorial, Cirq.circuit, and then just essentially throw in all these operations, and you'll get out an object that would look like this. So that's sort of the syntax, just how to do it. And then the question is, what can you do with this? So sort of what gates are around in Cirq. Here, I'll skip this section for a second. The common gates are the things you would expect, sort of looking at maybe a textbook or any other resource. So there's the poly gates, Cirq.x, y, and z. There's, for example, Cirq.x is a bit flip, Cirq.z is a phase flip, and Cirq.y is a sort of combination of the two, a bit and a phase flip. There's also rotations about these. So these, if you think about rotating about X, Y, and Z axes, these are for a particular angle. You can do it for arbitrary angles with Rx, Ry, and Rz. There's more special gates, which I'll just flash here. It's I don't think anyone's going to remember this if I talk about it, so I'll just mention it quickly. You can take powers of these gates, so giving them particular exponents, and then more standard gates like we've seen, Hadamard gate, the S gate, and the T gate. Both of these are special cases of the Z gate, Cirq.z, of particular exponents. So now that we see this, this is a good point to highlight the previous section. So gates in Cirq are very useful, and they behave like you would want them to if you were sort of writing it down on pencil and paper, which is to say that, you know, we might want to take a power of a gate, here a square root, here sort of fourth root, and this is all allowed. These are all operations. You can raise them to exponents. You can do things like multiply them to form tensor products, and other useful things like this. And of course, what we're talking about now is throwing them into circuits. So to throw them into circuits, you act on them with qubits and then put them into the circuit. But in general, these things behave like you would expect. So very nice functionalities. Now, before I get to the custom gates, let me define or briefly show the 2-qubit gates. As you might expect, controlled Z gate, and it can also be to a power, like we've talked about, C0, also to a power, and then swap gate, also to a power. Okay, I think that's enough gates. I don't see any questions in the chat. Were there any questions otherwise? I'll pause for a second.
So Ryan, I actually have a quick question. I'm coming from a circuit design background. I noticed, for instance, in your description of the circuit, it looks like you're describing a circuit from left to right, but when you say Adamar of B, you don't create a new point in space and time, because then you do C naught, and you don't do C naught of the Adamar of B, you do C naught of B again, right? So for a circuit design person, this is very confusing, because it looks like the input to the C naught is not the output of the Adamar circuit as is suggested by the diagram, but rather the input, which is the B. So see what I'm saying? My question here. So it seems to me that the Adamar acts on B itself in time and in space, so to speak, right? So it changes the state, if you will, of the B, and that is that modified state after being modified by H, that is the input to the C naught, right?
Yes, that's absolutely right.
Okay.
That's an interesting point. I guess I'm not familiar with circuit design as you're referring to it.
Yeah, because let me just say this, in a circuit design, you would call B as a point like a wire. The H gate would produce another wire with a different name, and like B prime. And if you wanted to put that output of the H gate into the C naught, you would say now it's a C naught of C and B prime, not of B, okay? So that's why this graphic representation for a circuit designer person and your textual description of this same circuit, there's a mismatch, right?
Mm-hmm.
Right. So just to, you might get some questions along those lines, like, oh, I don't understand why the input of the C naught is B and is not the output of the Adamar, right? So just to...
Yeah, thanks a lot for highlighting this. That's really interesting. So I guess it's different conventions in different fields. So the way it is here, I'll just note is, again, not a Cirq specific thing. This is just sort of the general language of quantum circuit diagrams. And so it's good to clarify, again, maybe just to emphasize this point. The sort of lines are always the qubits. And we start out, usually you start out in the all zero state. And then the gates are sort of operations happening on the qubit at a particular time. So in this example, like with Hadamard and C naught, we first apply Hadamard to this qubit, and then we apply the sort of C naught gate after that. So that's how I would read this diagram. But this is great to know. Thanks a lot for that.
Yeah. Okay. Thank you.
Yeah. Maybe wait another second, 10 seconds for any other questions, maybe in the chat.
For circuit design people, it looks like this H would be applied and it would be gone. And then basically, this is a timeline of actions, not a timeline of circuits, so to speak.
Mm-hmm, mm-hmm. Okay, good. So not seeing anything else in the chat. So let me go to the next tutorial, which is how to create custom gates. Custom gates, let me get back to the slides, are, well, there's nothing new here on the slides, so I'll just go back to the tutorial. But custom gates are, I've mentioned all these standard gates, and it's things, like I said, that you would find in textbooks. But when you use these packages, probably less so now, in the old days, there would only be like a few gates defined, and you would want to use something that wasn't in the language, and you would have to define your own gate. And sort of there were differences between these packages of how to do that. And I wanted to show how it's done in Cirq, because it's very nice in a very natural way, I think. So let's go back to the tutorials. And now in a new guide, before we were up here in gates and operations, now we're down here in custom gates, which is linked to at the end.
Okay. Ryan, sorry, I got this, there is this, you forgot to share by accident. I don't know if are you sharing the screen? No.
Oh, can you not see the tutorial, the website?
No, not the screen. Your image is gone, so you only have your photo. The screen we can.
Oh, sorry.
I mean, yes.
There we go.
Yeah,
How's that?
there we go. Thanks.
Okay, sorry about that. So now back in custom gates. So I think you can see this. Same thing, we can always run it in Colab. I'll just show the website for now. So here we import or install Cirq again, and we'll also use NumPy in this tutorial. So what is said here at the start is standard gates are described in this tutorial, which is the previous one that I was just talking about. And now the question is, gates in quantum circuits are just arbitrary unitary operations, or they can be. And now let's say we're faced with the problem, I want to use some unitary, I can't find it in Cirq, or maybe it's not defined in Cirq. What do I do? So that's what this guide is about, and we'll see how to do that. And again, very natural way. And I quite like this method. So we sort of do it the way any gates are defined in Cirq. And here is highlighting the general pattern. So there's sort of two steps or two options. We can inherit from Cirq.gate, and I'll explain what inherit means and what Cirq.gate is. And then we can either define one of these two methods, numQubits or QID shape. And then the part that we mostly care about is defining one of the unitary or decomposed methods. So I'll explain this, what I mean here. The other thing you can do is inherit from single qubit gate, 2-qubit gate, or 3-qubit gate. And these are just subclasses of Cirq.gate with a particular number of qubits. So let's see an example. When we start with a gate that we want to use, we start with its unitary. And maybe in Python, we represent it as a NumPy array. So let's say this is the unitary that we want to do. And we can't find it anywhere in Cirq. So what do we do? Here's the pattern for how to define this as a custom gate. So this part here, we'll call it my gate, very clever name. You can call it anything. What we do is we inherit from Cirq.gate. So that's the first step that I mentioned. And then this is all sort of boilerplate. This you would just copy and paste. This is a single qubit gate. So we define numQubits and we return 1. And that's how we tell Cirq it's a single qubit gate. And then the most important part is defining its unitary. So we do that. Again, the thing we know is it's sort of matrix representation as an array. And that's exactly what we do in this method here. Maybe I'll pause here to see if there are any questions. No questions? Good, so that's the meat of it. There's another thing you can do, which is say how it's defined or displayed in a circuit diagram. So we do that with this method here, circuit diagram info, and we can return a string, which is how it appears in a diagram. For example, the Hadamard gate would return H here, and that's how it's represented. So let's see an example of how to use this and how it appears in a circuit. This is the syntax for creating a circuit, which I mentioned in the last tutorial. And then after we create the gate here, we can use it like any other gate in Cirq. So again, we add operations to circuits. And when we add operations, they act on qubits. So here we see some variety. Now I'm using a line qubit, and we throw that into the circuit. And then if we print it out, we see this diagram here. And it's a custom gate. We see the symbol G because that's what we defined here in the circuit diagram info. Okay, so now let me skip how to simulate circuits and that in the next tutorial. The other pattern for creating or defining gates is inheriting from, say, 2-qubit gate, like I mentioned. And when you do this, same pattern, but now we don't need to define the number of qubits. So that's built into the 2-qubit part here. And here we just define the unitary. So 2-qubit gates have 2 symbols in their circuit diagram info, a top wire and a bottom wire. And let's see how that looks when we make a circuit with this gate and print it out. So here, as you can guess from the names, we see the symbol that goes on the top wire. So that's first. And then the symbol that goes on the bottom wire. So that's second. Any questions here about custom gates?
Yeah. So I have a quick question, Ryan. So it seems to me that the way you describe, the way you're building this circuit, if one can call it circuit, is you're sequentially going from one statement to the other. And where the gate lies is on the qubit that's associated with that statement, right? So essentially you, and that's why there's potential a lot of mental complication here for people who are very used to the circuit design world, because I think what you're doing is you're sequentially going from top to bottom, laying out the operations that happen in time for a specific qubit. And so that's how time progresses. Okay, so that was my first observation. So this second 2-bit circuit, so what's the meaning of that vertical bar there, if any?
Good question. These are to denote that just these symbols are sort of connected.
Okay.
So if this wasn't there, you could interpret that as 2 single qubit gates.
Right. Okay. I got you. All right. I understand. Yeah.
Ryan, there is one question in the chat.
Yeah. In the Zoom chat?
Yes. I can read it out loud if you want.
Okay, that would be great. I don't
the question is, what is the star symbol in the circuit creation call?
Oh, okay. So this is the unpacking operator in Python. Completely Python thing, has nothing to do with Cirq. But here, the gate acts on 2 qubits. So we unpack them here. This is a list of 2 line qubits. And the star is just unpacking them. Yeah, good, great question. Yeah, I'm trying not to go too fast now. So I think it's a lot better to explain things more in detail. So if anyone else has more questions, please ask. I'd rather do that than flash through a bunch of material that maybe no one's digesting. So. Okay, if not, let me actually mention how to simulate circuits. And I can do it in this tutorial. It's done here. So the way this is done in Cirq is very simple. You can see it just in 2 lines here. So the general pattern is I need to get an object that will simulate circuits. And the standard one in Cirq is appropriately called Cirq.simulator. So that's this guy here. And then when you have a simulator, you can call one of 2 methods on a circuit. you can call the simulate method, as I do here, and I'll explain what that is. And you can also call the run method. So instead of simulate, I can do sim.run. So what's the difference? The simulate method will sort of assume full knowledge of the state. And that means that if I simulate it, it will give me like the output wave function. And we can see that here. There are no measurements in the circuit. And here I get the output vector, output wave function, written in this nice Dirac notation here. So if this isn't familiar to people, this means that this is a 2-element vector. 0 is the vector 1, 0. 1 is the vector 0, 1. So these are just the basis vectors. And then these are the amplitudes here. 1 over root 2, 1 over root 2, minus 1 over root 2. Now, the other method that I mentioned is run, sim.run. If I use that, then this is sort of what a quantum computer would actually do. So I wouldn't have any knowledge of the state vector anymore. I would only get measurement results. So when we actually run circuits on hardware, this is all we get, right? We have circuits. Let's see if I go back to this diagram. We have circuits, and then we operate on our qubits with gates. And then at the end, we measure. So these are measurement operations here. And when we measure, we get 1 classical bit for every qubit that we measure. So back in this guide, if I called sim.run here, well, one, I would need to measure something first, and then it would return what the measurement results are, not the final state vector. Any questions about this?
Yes, there were a couple of questions from the other forum. Let's see if we can organize them. Because it's a little bit.
We have actually 2 questions. I actually can ask Mafalda to unmute and ask the question herself.
Yes.
Okay.
I tried to unmute her, but for some reason didn't work.
Yeah.
Mafalda,
Hello.
do it now.
Hello. Can you hear me?
Yes.
I was wondering if in the event that we would want to do, for instance, parameter sweeps, if it would be possible to construct a gate that will receive some arguments and use them to build a unitary matrix parameterized a certain way.
Oh, great question. So that's a later part of the guide, which I didn't get to, but I can mention it here. So thanks for asking that. I didn't pay for that question, but I can answer it here. So the answer is yes. You can define gates with parameters. These are common things. So here's just a rotation gate with a parameter theta. And again, you do it in the same way, but now this gate, when I initialize it, has this parameter theta now. And then the actual unitary itself uses that parameter. So this is defining in Python exactly what you see mathematically here. So cosine of theta, sine of theta, etc., all the matrix elements. And then this is, again, another valid gate, and we can use it just as it is expected in Cirq. So to instantiate it, I give it what the angle theta is. And I'll mention you can also use a parameter here. A parameter means in Python like a SymPy symbol. So I could do import SymPy, SymPy.symbol s, and then I could throw that in here. So that's just a symbolic value, and I would give it a value later, is essentially what that means. But other than that, exactly the same. Gate acting on qubit, printed out in the diagram, and we see it here. Yeah, great question.
Yeah, I think there was another question from Vincent.
Yes, I was wondering that when you are simulating the custom gate, why are there no measurements? Is it because you don't have a measure gate, or?
Oh,
why?
yeah. That's exactly it. It's simply because we didn't add any measurement gates to this circuit. Here we only added the custom gate that we defined. If we wanted to add a measurement gate, we could do that in the same way here. We would just do like circ.measure this qubit, and then we would have that when we create the circuit as well. And then you would see in the diagram a measurement operator that looks like this.
Okay.
And at that point, we could run the circuit.
Okay, that's
Good.
thanks.
Yeah, great question.
Okay.
Okay. How are we doing on time? I think 15 minutes left.
Yes.
Okay. And should I?
No, go for it. I mean, we started at 35, so at this point, we have yeah. Go ahead. We have 10 minutes left. It's okay. Let's go. I mean,
Okay,
people are engaged. Are interacting. I think this is good. We can basically, obviously, take a few minutes extra. It's fine.
Good. So let me talk about noise then,
Yes.
and how to simulate circuits with noise. So let me just explain what noise is and how it's represented in Cirq.
Ryan, can you share again your video, please?
Oh, sorry, it went out.
Yeah, you went away.
Thank you.
Can you see it now? No, you can't.
Not yet.
Uh-oh. It says my video is on now, but you still can't see me, yeah?
That's right. Well, it's okay. I mean, you can continue if there is any issues with your video. I mean, it would be nice to see you, but I don't think it's a big issue.
Okay, sorry about that.
No problem.
Hopefully it will kick back on.
Yeah, we'll kick back in.
Okay. It's still me though.
Yes.
Noise. Noise in Cirq is always represented by cross operators. So when we had unitary gates before, this is a channel with only one cross operator, and that cross operator happens to be unitary. In general, maybe people haven't seen this before, but the general evolution of a quantum state is a channel, what we call a channel. Some channels are unitary, but some are not. The ones, well, every channel can be described in this representation. So the state, the density matrix rho, gets mapped to sum over k, ak rho, ak dagger, where ak are the cross operators. So you can uniquely specify any channel by saying what its cross operators are. And the cross operators themselves may not be unique, but I say this because this is how we define noisy operations in Cirq, essentially by saying what the cross operators are. And then you can use them as channels and then add the channels to the circuit. And in that manner, you can simulate noise. So if you want to know more about the theory, maybe you can read these lecture notes here, but I'll just talk about how it's done in Cirq, unless there are any questions just about the sort of notation or setup here. Let's give an example. I think that'll help. So an example is a commonly used channel, which is the bit flip channel. And just like standard gates, standard channels are already predefined in Cirq. But like custom gates, you can define any channels, like I said, by mentioning the cross operators. But here, let's look at this standard bit flip channel. So what does this say? This means that with probability P, we apply, or a bit flip happens on the state. And with probability 1 minus P, nothing happens. So that's how we read this here. And so let's say we want to use this in Cirq. How do we do that? We've seen how to use gates before, but what about general channels like this? The way you do that, very similar notation. So like we can create a gate, we can create a channel, here in this example, the bitflip channel, by calling cirq.bitflip and then telling it what the probability parameter P is. Anytime you have a channel, or any gate actually, you can always get its cross operators. You can always get the cross operators of any channel in Cirq using cirq.channel. And an example of that is here. So I have the bitflip channel that I defined. I call cirq.channel on it, and then the rest is just Python syntax. But this tells me what exactly the cross operators are. So the first one is this guy. And we see this as proportional to identity, as we would expect here. So there's a sort of implicit identity on either side of the state row here. And then the second cross operator is proportional to poly x. Poly x is 0, 1, 1, 0. And then here we see the probability parameter P factoring into that, as we see in this equation here. It's not 0.1 like we defined. It's, I don't know, like maybe the square root of that or something so that it's properly normalized. But that's why it's 0.3 and not 1 here, like it would be for poly x. Okay, so now we have an example of a channel. And then, like I said, to simulate noise, we add channels to our circuit. So the way to do that is just like gates in Cirq. So the syntax is the same, exactly the same. Here we get the number of qubits that the channel acts on. That's just an example. You can do that. And then here we create a circuit with a bitflip channel on each qubit, and the qubits that we use here are line qubits. So when we print this out, we see 3 qubits, bitflip, BF for bitflip, with probability 0.1. So this, for example, you might want to use to model state preparation errors in a circuit. So this says that we start in the 0 state at the far left here. All qubits 0, 1, 2 start in the 0 state. And then with some probability, they flip. So maybe we prepare the qubits incorrectly. There's some error that occurs. That's how you would model that in Cirq. Questions about the fundamentals here?
I don't think there are any questions, Ryan. Yeah, let's. I don't know if you have something in simulation to show us, like an example.
Yeah, absolutely. Let's see that.
I think it would be great to kind of wrap up this session, this tutorial, with an example, and then people, and then also suggest people if they want to explore other examples where to go online, right?
Yeah. Okay. I'll do that quickly in 3 minutes now.
Okay.
So the next example here is just saying that, like gates, channels can be controlled. So that might be a useful thing to have correlated errors if you want to model that. Here is other common channels that are already defined in Cirq. For example, we have the bit flip above. There's also phase flip, phase damping, and amplitude damping noise, all these other ones. Depolarizing, that's a common one. This is a good place to mention the API reference for Cirq, which I haven't yet, but let's do it here. So if you click on any of these links in the documentation, it will take you to the API reference. So still on the Google AI Quantum website, now on the API reference. If you need to know what something is in Cirq, this is where you go. It tells you what it is. You can view its aliases. So depolarize, ops, common channels, depolarize, all the same thing. And then it tells you how to define it. So you see its signature here. And then even really nice, tells you where it's used and what tutorials. So introduction, and also the noise tutorial, which is what I was talking about a second ago. And then there's just more doc strings and examples, arguments, things like that. So API reference, very helpful if you want to continue exploring in Cirq. This is a great thing to know about. Quickly, since it was asked, let me just show an example of simulating this. Simulating noise, there's sort of 2 ways you can do it. I'll skip over the custom channels. If you want to see how this is defined, I encourage you to read over this tutorial, maybe after. And let me just get to the simulation, skipping over some more things. So there's 2 ways to do it. One is to use a density matrix simulator, like storing the full wave function. This will store the full density matrix. So you have the ability to apply any channels here, because they can also sort of always be done if you're storing the density matrix. So here, create a circuit, and we print it out. So this is the circuit that we want to simulate. It has 1 channel in it, which is an amplitude damping channel. Now to simulate it, similar syntax from before. Now instead of simulator, I use density matrix simulator, and I call the simulate method again. So simulate with density matrices will allow you to have the full density matrix. Running will only give you measurement results. So if I call this, I get the final density matrix, which we can see here. So that's one example of simulating noisy circuits. The other example is still using the Cirq simulator. And this is a really nice feature. Instead of storing the full density matrix, you can do it just by storing a wave function, and it will by default, if it sees any channels, default to Monte Carlo simulation. So what does this mean if you haven't seen it? Every time you hit a channel, you apply one of the cross operators with some probability. So in this example, when I ran it using the wave function simulator, no bit flip was applied. If I ran it again, we might see that a bit flip was applied. So I would get out the one state as our final wave function there. Okay, that's all I'll say about noise. And then let me just go back to the slides to wrap up. So we made it through gates and custom gates, so that was good. We made it essentially all the way through noise. So we saw cross operators, this representation, and then we saw common channels already defined in Cirq. If you want to define your own custom channels, you can also do that in a similar way that gates are done. And let me quickly flash the Cirq tutorial. So like I said before, all, or at least most, of the very nice publications coming out of the Google AI Quantum team have associated documentation and code that you can run yourself and reproduce the results. So one example is the Fermi-Hubbard experiment, which is on arXiv, came out just late last year, I believe, late 2020. And you can read the paper here. You could also click on this code link, and the code link itself will take you to this experiment example where you can actually reproduce this plot. And this plot is something exactly from the paper. So that's very nice. And you can dig in as much as you want, see how Cirq is used, see how other libraries are used, etc. So these are all, just wrapping up now, the links that I mentioned. Again, your sort of landing page, quantum.ai.google, and for software, go to software. The things I mentioned were the guide and the tutorials. Also the API reference, again, very useful if you're playing around in Cirq and need to know what something is or need to search for something. Please use the API reference, it's very helpful. And then Cirq was the last thing that I mentioned. So you can see the Fermi-Hubbard experiment there, also the QAOA experiment, and other ones. There's also quantum chess there, which is quite interesting. You can learn more about that. And I mentioned them briefly, but at the start of the talk, let me just provide links to them in case you want to look. So we talked about simulating circuits, simulating noisy circuits. There's default ones to do that in Cirq, but there's also an external library called qsim, which contains some very fast and highly optimized simulators. So you can check out QCim. If you're interested in chemistry, any chemistry applications, OpenFermion is the place to go. And then if you're interested in any machine learning applications, TensorFlow Quantum is the place to go. Okay, so I think I can maybe wrap up here and then stay around for questions.
Okay, thank you very much, Ryan. So there's at least one question, I believe, from João Fernandes, no?
Yes, yes. Yeah. Can you hear me?
Yes, go for it.
Thank you. Great talk, Ryan. Thank you very much. I was just wondering, can you tell us a little bit about the, I guess, quantum machines on which these circuits are being executed, or whether the circuits are being, say, simulated, and how we can, say, from the code specify that?
Yeah, absolutely. Great question.
Thank you.
Let me show that here. So here we were always using simulators. If you want to see how it's run on actual hardware, you can go to, still down here on the website, the section about Google hardware. So this will tell you, and this is all open source stuff, so it will tell you essentially what you need to sort of get access to it. Right now it's sort of in what's called an early access program. So particular users sort of working with Google to run experiments now. And let me show actually quickly a good example of this in the Fermi-Hubbard experiment example. So this is the one in Cirq that I mentioned. And this has the option in the notebook of running it on hardware or using a simulator. And it's at the very end, so I'm going to scroll quickly here, but I just want to show sort of the syntax and how it differs or how it's similar. So the only thing that's different really is these lines here. So this is at the very end, execution on Google's quantum computing service. And it tells you what you need. You can see how to do the setup in another tutorial, but basically you need this environment variable called Google Cloud Project, which you can create if you have sort of the valid credentials. And then we get sort of the analog of the simulator. So this is what I was showing here, Cirq.simulator. If you want to replace that with the actual engine, there's really only one line that you change, which is this. So here, instead of using a simulator, we get an engine sampler. So in Cirq, it uses a name sort of engine or quantum engine instead of the simulator. So that's the running on an actual quantum computer part, hardware part. And here you can see we give it processor ID. So that's just the name of the particular processor. Here it happens to be Rainbow. And then we also give it a gate set that we want to use. And here you can read about different gate sets in the Google hardware docs. Here we use the square root of ISWAP gate set. So sort of the syntax of it in Cirq is essentially identical. You just swap out a simulator for an actual quantum engine, and then things are the same.
Okay, any other questions from the audience at large?
Yes, I have a question. It's similar to the previous question, but for example, in the IBM's computer, you have to take into account the coupling map that represents the qubits. So I was wondering if Google has the same technology, or you don't have to take into account the coupling map?
Good question. So you do. Most of, well, let's see. The answer is yes, you do. I don't know how much I can say beyond that, but.
But there's a mechanism for you to specify that, right?
Yes, so you can get sort of a device. This is a common thing. in Cirq, a device has a set of qubits with a set of connectivity constraints or coupling map, as you say.
Right.
And to run on the device, you need to respect that coupling map. And if you don't, you can, there's tools to sort of compile the circuit or do routing so that it will. But the short answer is, yeah, you still need to respect that.
And so kind of connected to that, the real quick question that I had is, well, hopefully quick, how big are the circuits that you can simulate at this stage? I mean, is this a heavy simulation or not that complicated?
Oh yeah, great question. So if I go back to the slides, I think you can see on the page here.
Yeah.
The number of gates is really quite impressive in these experiments. So here, this is from the website as well. The Fermi-Hubbard simulation, which again is that notebook. And if you look at the docs, you can see exactly the circuits that were run, but it has over 1,000 gates.
Gotcha, right.
Which is quite good. And there's ways of sort of getting to that many gates, doing calibration and things like that, which are described also in the docs. But this is like a rough ballpark number for some of these experiments.
Right, but how many qubits, right? In the hundreds, max?
Yeah,
or just like that?
less than hundreds. The Fermi-Hubbard experiment was, I believe, 16.
Okay, right.
The 2019 supremacy experiment was
gotcha.
52 qubit chip, and I think the OTOC experiment was also one of the full chips, so like 50 qubits. Gotcha. So max like 50 qubits. And like 1,000 gates at least.
Gotcha. All right. So that's kind of the state of the art in terms of realistic simulation, so to speak.
Yes. Yeah, I would say so.
Okay. All right. Thank you.
So in Cirq, we are able to simulate up to 60 qubits.
Where? I'm sorry. It's Vincent, right?
In Cirq, we are able to simulate up to 60 qubits.
Using like the Cirq simulator, you mean?
Okay.
And then I have another question, which is, does it exist the reset gate? I mean, can you simulate a qubit and then reset it to the non-excited state and reuse the qubit?
Great question. You can. That's a commonly defined channel in Cirq. So Cirq.reset is what will do that there.
Yeah.
Okay.
Yeah, good question.
Okay. I mean, I think unless there's a real quick question now, I think we're done. We're past an hour. So any other questions?